Okay, hello. It's 10 o'clock, so well, 10 o'clock where I am, so let's get this thing going. Happy Friday, everybody. Hopefully, this is live and you can hear me. Hello, welcome to another edition of the Cool Stuff live stream. My name is Aaron Patterson. I am your host for today on my live stream because it is my live stream, so I am the host. Happy Friday to everybody out there. Um, oh hi, hello Marco, hello Taylor. What was I gonna say? I don't know. It's good to do. It is good to do live stream. Thank you all. Thank you all for joining me and helping me to amortize the cost of my green screen. The more of you that watch, the lower the price is for the green screen. So I appreciate it. Let's see. I guess let's get started. Enough of my shenanigans. Let's do some stuff today. Here's our keynote presentation for today. Today we're going to be hacking on the Prism Compiler. We hacked on the Prism Compiler last month with a Gemma. We're going to do it again this month. But this time we're going to have Kevin on. And I had made like a whole bunch of slides last month that we didn't use, like we didn't get to them, and I felt that was kind of a waste. So I'm gonna do them this time. We're gonna use those slides this time. So as always, if you have questions, put it in the chat. Feel free to ask anything, and I will answer it to the best of my ability. So I guess let's get started. Come here, keynote. Happy Friday, everybody! Woo! We made it. Another week down the drain. Last month we hacked on Prism, and guess what? We're gonna do it again this month. This month we're also gonna hack on Prism. Woo! Um, last we covered AST to bytecode translation last month, so we're not gonna do that this month. If you want to learn about going from AST into bytecode, go watch the live stream from last month. We're just gonna build on top of that knowledge this month. This month, what we're gonna do is we're gonna hack on a Prism compiler bug. So we're gonna look at a Prism compiler bug and try to fix it. But before we do that, we're also gonna take a look at Ruby's calling convention. So we're gonna learn about Ruby's calling convention. We're also going to learn about local variable storage. I figured, like, since we're talking about the calling convention, like, we should also take a look at local variable storage. And the reason we're going to do that is because parameters to methods in Ruby are also treated as locals. So it's important for us, like, if we want to understand how parameters work, it seems like a really convenient time for us to also learn about how local variables work. Then I'm going to bring on Kevin. We're going to talk about some stuff. We'll talk about Prism. I don't know, talk about whatever. And then hopefully we will fix this bug. And if this bug is too easy and we fix it very quickly, then we'll like look at another bug which is more challenging and maybe we can't fix. So I want to make sure, gotta make sure we end the live stream on a high note by having a bug we can't fix, right? Wouldn't want to disappoint anybody. So this is the code. Like, this is the code we're going to be looking at today. We've got a method that takes keyword parameters, and some of them are required. You'll notice here, like B and D, they're required, and then A and C are not required. Those have default parameters, and we're just going to call the method only with the required parameters. So if we try running this code with just normal Ruby, it works, and you see the value is an array 1, 2, 3, 4. Hopefully that font is big enough. If not, don't worry, we're going to run it in a terminal with a big font, so you'll see it. If we run it with Prism, though, it just blows up and says, like, hey, we're missing a keyword A, gives us an argument error and doesn't run. And the reason, like, this bug is due to a calling convention mismatch. So we'll take a look specifically at what that mismatch is when we go in to fix the bug. But that is the issue. So I guess like when we say calling convention, that kind of begs the question, like what is a calling convention? Calling convention is simply just an agreed upon way for calling methods. So it just means that functions expect their parameters to be in certain places, and uh, they expect that when somebody's calling the function, you'll put those parameters into a certain place, and then when the function returns, the return value will also be in a certain place. And this convention is like totally made up, and anyone can define any calling convention that they want. But like if you want to work with other languages or work well with other libraries and stuff, then you everybody should use the same calling convention. But it is in fact just a made up thing. So for example, x86 machines have their own calling convention. And if you go read a like I've linked to a PDF on the calling convention here at the bottom. I find this thing really, really handy, especially when working with YJIT or any type of compilers. It's handy to look at the calling convention for x86. Basically, the calling convention for x86 says that parameters should be placed in certain registers. So, for example, the first parameter needs to be in the RDI register, the second parameter needs to be in the RSI register, etc., etc. And then the x86 calling convention says that the return value is in the RAX register. And of course, like ARM64 also has its own calling convention. Its calling convention is basically says like all the parameters should be in the X0 through X9 register. So the first parameter is in the X0 register, second is in X1, etc., etc. And then the return value must be in the X0 register. Now, Ruby, YARV, also has its own calling convention, but since Ruby is stack-based, it doesn't have anything to do with registers. So x86 and ARM, those are they're a register-based processor. Ruby's virtual machine is a stack-based machine, so we have to do everything with a stack layout. And Ruby's calling convention basically says, hey, all the parameters need to be on the stack, and then the return value needs to be on the stack. So for example, if we have this Ruby code here, the caller foo, like down at the very bottom, that code at the bottom, it's just going to push 1, 2, and 3 onto the stack, and then call the method foo. And then the callee foo, it expects that 1, 2, and 3, or it expects that the values for A, B, and C will be on the stack, and it corresponds those with 1, 2, and 3. So we're going to take a look at this a little bit in detail. Like we're going to look at Ruby call frames, and we're going to see how they work together. So the question is what happens when we call a method? Like practically speaking, I want to discuss what happens when we call a method and how locals are associated with particular values. Because as I said, parameters are also local variables. So here we have a method with three parameters plus one local variable inside the method body. So the question is what happens when we call this method? And the other question is how are locals associated with particular values? So to understand the answer to this, we just have to take a look at Ruby's stack layout. So Ruby has two stacks. We have a call frame stack, and then a stack of values. So local variables are stored on one stack, and each call frame in its own stack has two pointers, the environment pointer and the stack pointer. Now the environment pointer is constant, and it never changes for the lifetime of the call frame. So it stays in the same place always. Now the stack pointer, it has to move up and down as we're pushing and popping values onto the stack. Now, in order to fetch a local variable, all we have to do, oh yeah, I made some really cool animations. I gotta use those. All right, so we push something onto the stack, yes. And then the stack pointer moves. And then if we pop something off, we push another thing onto the stack pointer moves. If we pop a thing off the stack, then the stack pointer moves again. But for the entire lifetime of the frame, the environment pointer stays in the same place. So it's always in the same place. Now to fetch local variables, the local variables are just negative offsets from the environment pointer. So all those like the callees stack is shared with the callers stack, and all those values, those local variable values, the parameter values, they are just negative offsets from the existing EP. So for example, we have here this code. The instructions on the left hand side come from the method that's in the upper right. So that hello method with the D. Oh, hello, woo! D equals A plus B plus C. So on the left-hand side, we've translated that Ruby code into the YARV instructions, and we're going to walk through it and see what happens, like see how it actually executes. So first thing we'll do is we're going to say, hey, we're going to get local on -3, and then we'll say get local on -2. We pop those off to add them. Then we we get local on -1 for C. We pop those values off to add them. Then we get the local value for D, or set the local value for D, then get the local value for D, do our multiplication, and then we leave. Ven is asking, how do you get the names back for debugging purposes? A mapping of, they're asking, is it a mapping of offsets to names? That is exactly what happens, and we're definitely going to look at that. That has everything to do with our Prism bug and what we're gonna fix today. But yes, all the local offsets are mapped back to names, so we can figure that out. That's how debuggers can figure it out. So we have these indices here, like we have these negative offsets into the EP, but like the question is, how do we, like, we're referring to a local variable, how do we figure out what that index is? And the good news is that the compiler, Prism, figures it out. So the Prism compiler figures out those offsets for us. And the thing is, though, we want to have like really convenient offsets. So for example, like, how did A, B, and C get mapped to the values that we passed it? We in order to understand that, we have to look at the caller and callee relationship. So here's our original code with A, B, and C. We're adding all those together. Let's take a look at the caller side of the equation. We looked at the callee side, how we actually fetch those local variables, but let's look at the caller side. So what happens when we call this method? Like, what exactly happens? Well, the first thing we do is what are we doing? Okay, right. So the first thing we do is we push self onto the stack. And that's because, like, when we're calling the hello method, we have an implicit receiver, which is self, of course. All methods have a receiver. And in this case, we've just omitted self. So we push self onto the stack. The next thing we do is we push the parameter 1 onto the stack. So we push 1 on. Then we push 2, of course. Then we push 3. And then finally, we send the method call hello. So when we do send, the virtual machine pushes another call frame onto the call frame stack. So now we have 2 call frames on our call frame stack. And that new call frame points at the previous call frame, and that's actually how we can get stack traces back out. So you'll notice our top call frame, it has a stack pointer that points underneath 3. And we have a new frame here. And this new frame, it says, well, we know that we have 3 locals, which are the parameters A, B, and C, but we also need storage space for D. So D needs a place to store its value. So when we push that new frame, we actually allocate 1 extra slot in the stack for D. Then underneath D, D becomes our, like, the bottom of D becomes our EP, and then C is a -1 offset from the EP. So when we start out here, our EP and our SP are the same. All right. So just to repeat, when we're ready to call a method, our stack looks like this. So we have self and then 1, 2, 3. Then the stack for the previous method becomes the environment, or the EP, for the new method. So we push our frame, we point the EP at the bottom of the stack, and then we have our values and we execute the method body itself. So yes, great. We executed it. Great. So this value, like this space here, my head is kind of in the way. This space here where we have A, B, C, and D, we call that our locals table. So that's a table of locals. In this area, so Prism calculates that size for us, and that's how we know like how much space we need to allocate for the locals table. So we have here like A, B, the storage space for A, B, C, and D. And you can see here, like, we have 3 parameters plus D. Those are all of our locals. So that's how we're able to figure out, like, the size of that storage space that is required. So every time we push a frame, we know that there are 4 locals, 3 of them are parameters, and then we have to push 1 extra slot for the D, like the D local. So the compiler knows, it looks at all the local variables and it says like, okay, I have a certain number of parameters and then we have a certain number of extra locals. So when we push a frame, we need to push enough slots for that. Now, keyword parameters, like we looked at positional parameters and we're going to talk about keyword parameters. They're a little bit more complicated, I guess, but we still basically use the stack. And we're going to do that. We're just going to do that on the terminal. But before we do that, I am going to bring on Kevin, and we're going to talk a bit about Prism. So let me figure out how to do that. Did I do it? Where is OBS?
I think you did.
I did it. Hey, I see you.
Hello.
Hey, Kevin, how are you doing?
I'm good. How are you?
I am doing well. Oh, everybody watching the live stream, if the audio levels are off, let me know and I will adjust them. I did my best to make us the same, but I don't know if they are. Kevin, welcome. You are the inventor of Prism.
Yes, I suppose. Yes.
Yes. Okay. Well,
Yeah.
you started the project, right?
I did. Yes,
Okay.
I did.
Great. Why did you start this project? Like, I know Ruby parsers
I don't know.
You're a glutton for punishment. Is that why?
Yeah, exactly. Actually, it's really funny. I have a funny anecdote about this. I don't know if you remember, but like before I pitched this project, I asked you about it, and I was like, should I write a new parser?
And I said no.
I think you said something to the fact of like, see you in 30 years. Like, I think I was like, cool. Awesome. Yeah. So, yeah, no. Okay. So, I mean, there is a bit of an origin story. I was working at a startup a couple years ago. I guess it was like 5 years ago now. And I wanted to write a formatter for Ruby because one didn't really exist in the ecosystem yet.
Okay.
And I wanted to use the standard library so you didn't have to install any gems. And I wrote one based on Ripper. Well, actually, my first iteration was trying to use regex because I didn't know what a parser was.
Okay.
And then I learned about Ripper, so I started using Ripper. But I had all these like subtle bugs because like Ripper doesn't provide a ton of information to you. It basically provides the nodes, but not like the tokens or like a lot of location information.
And for people who don't know, what is Ripper?
Yeah, so Ripper is a standard library that came around in Ruby 1.9, and it provides you hooks into the existing Ruby parser such that you can get notified when something, in the weeds a little bit, but it's called when a production rule is reduced. But basically, it's whenever you find an inner node in the tree, you can get a notification, and then you can use that notification system to build up your own tree.
Okay. So it's basically a parser that's built, like a Ruby parser that's built into Ruby itself.
Yes and no. So it has its own parser that builds its own tree, and then it also has kind of a bare Ripper which provides nothing for you. So you have to build your own tree yourself.
Okay. So it just gives you the parse events, and then you say like, yes, hey, I'm gonna assemble my own tree.
Yeah. So most people use Ripper.sexp, which is S expression, which gives you just an array of arrays like all the way down. But I took the approach of like building my own AST with objects. Actually, I used hashes first because at first I translated it all into JavaScript and then did all the formatting in JavaScript. And then I came to Shopify and I was like, we should use this formatter. And Raphael was like, I'm not using a Node project. I was like, okay. It's like, okay, my bad. So I rewrote it, and I rewrote it in Ruby, and that was called syntax tree.
Mm-hmm.
And I basically ported Prettier's algorithm for formatting into Ruby.
Okay.
So then that was the syntax tree formatter. But I still had like all of these massive amounts of problems that were like problems caused by Ripper. And then I pitched Ufuk, my manager, on like, hey, we should rewrite the parser. And he said no. And
Okay.
And then pattern matching came out.
Uh-huh.
And like all this other stuff came out, and Shopify was investing in Truffle Ruby, in the parser gem for some things, in syntax tree for some things, and in sorbet and CRuby.
Mm-hmm.
And all of these, it was like 5 parsers that had to be updated because of pattern matching.
Yeah.
And everyone was like going through like hell for multiple months to like all of these parsers had to be updated. So then he was like, oh, okay.
Makes sense. So
that is the origin.
Okay, I get it.
Yeah.
I get it. So we had pattern matching was introduced, and then that's how we got Prism. Got it.
Basically. Yep.
So what are the goals of the project?
Yeah. So when I started Prism, there were 10 actively developed Ruby parsers in the ecosystem,
Mm-hmm.
and like we don't have a large ecosystem, and that's too many. Like per developer, that was a way too high of a ratio.
Mm-hmm.
Because it was too many hours being spent by people who could also be contributing to like the main. If it were like one, like we need to consolidate our efforts.
Mm-hmm.
So the goal was to Sauron the various, the one ring into the one effort,
Right.
so that everyone could use it. But also just to like revisit it. It's one of those things that like, it's a large project. Like the parser is a large project, and it's just kind of been like, stuff has been added on over the years,
Mm-hmm.
and like going back and rethinking the entire design and rethinking how the AST should be structured is not something that generally happens for something like that large.
Right.
So the goal was to make it portable for everyone, to have like a really well documented thing. And then the other big massive feature is error tolerance.
Okay.
So error tolerance refers to the ability to continue parsing even in the presence of syntax errors.
Mm-hmm.
And that's table stakes for a parser that powers an IDE.
Mm-hmm.
So
right. So
that was what we built in from the ground up.
So you want to be able to use this parser for building something like a language server where people are writing stuff in their editor, and they're not done writing the program, but you need to the parser needs to be able to parse it even though it's like a half-written program, right?
Right. So most of the language server features, you don't want to just start them on save. Like you don't want to wait for like a stable state. You want to be able to introduce them as they're typing. Like type ahead, autocomplete. There's like a lot of stuff that you want to have that requires you to be able to parse something that has syntax errors in it. Yeah, not completed.
So the original, like the parser that ships with, I guess I have to rephrase that. The original parser for Ruby is a Bison-based LALR parser.
Yeah.
And you chose for Prism to do a recursive descent parser.
Yes.
Why did you choose recursive descent?
Yeah, so that's a great question. LALR parsers. Okay, so there's a lot of stuff going on here. Basically, in the 90s, when the early 90s and when Ruby was written, everyone was using Bison. Well, everyone was using Yak, which was the predecessor of Bison. And Mats chose that, and it made sense. That was what everyone was doing. And everyone was taught that in school, too. That was like the theory. If you look at the Dragon book for compilers, the guy swinging the sword at the dragons, it says LALR on the sword.
Yes.
It's like ridiculous. Anyway, parser generators were all of the rage. But at the time, especially then, there was absolutely no error tolerance. You could not easily recover from errors. There was something called panic mode, where it would just start to drop tokens until it got to something called a synchronization point. So you could like start to build it in. You could do error productions. There were ways to do it, but like it required a lot of manual work, and it became very difficult to maintain. Somewhere in the early 2000s and further on, everyone started switching over to handwritten recursive descent, specifically for error tolerance, but also for performance.
Okay.
You have a lot more control over the reliability of the performance of your parser, because generated parsers use jump tables, and they just jump around to various functions, and it's just like a massive lookup table.
Yeah.
And it's basically obviating a lot of the work that a processor, a smart compiler, can do these days. And when I say compiler, I mean like the C compiler that's compiling the parser after it's been generated.
Right.
If you use small functions, C compilers since the 90s have learned how to inline, and there's branch prediction, and there's all kinds of good things that processors can do these days to make it much more efficient. So the jump tables are actually fighting against the processor.
Right. So the original Yak or a Bison based parser is generating these. It's basically a state machine, right?
Yes,
and
it's a giant state machine,
and it's interpreting, like, it has to interpret that, use these jump tables to figure out where, like, what thing to go to next.
Yeah.
And the CPU can't necessarily predict that. It's not as predictable as just a handwritten recursive descent parser.
We also have significantly more control over the parser, because we have small functions that you can test and run, and if we want to change, the thing is with a grammar-based parser that's generated, sometimes you could unintentionally introduce syntax you don't mean to. For instance, there's a bug that was just opened yesterday on CRuby about, you can use in the target position for, like, in case of a rescue reference or multiple assignment or a for loop, you can use foo and then square brackets.
Can you say what a target position is? We're using jargon here, and I want to make sure people understand.
Let's say multiple assignment. Okay. Like, you have like foo comma bar equals whatever. And when that happens, Ruby will expand the value on the right side of the equal sign to spread it out over the values on the left side.
Right.
So those values are being, like, indirectly written depending on the amount of values in the runtime. So that's like a target, and you can put local variables, instance variables, a whole mess of stuff, constants. And one of the things you can put is, like, we call it an index, which is basically any method call to the square equals method. Square brackets equals
so
method.
you could have a, boy, maybe we should switch to a terminal. Well,
assume it's a hash that you're assigning to.
You could be like a with a square, and then on the left-hand side of it, you could have a whole bunch of those as commas separated, then an equals, and then a splat out.
Yes. Yeah. So a square brackets, and you can put anything inside the square brackets. So imagine if it were like a hash, be like a with like the symbol foo. Maybe we should switch to a terminal real fast.
Yeah, but sure. You want to do it? Yeah. Okay. Let's get a terminal.
Okay.
So, like,
here, let's do IRB.
Oh, IRB. Okay. You drive. Oh, wait.
Let's change for these.
Yes. All right.
Great. Okay. So let's assume we have some. Is it working? Okay. Yeah. Let's assume we have some hash like this, and then we have some hash of foo, and then we just want to assign the first value there.
Okay.
So now hash has foo points to 1, right? Because this anonymous splat took care of the rest of the values. Does that make sense?
Yeah. It makes sense. I think my pro tip is, like, people don't do that.
Well, yes, don't do that. But here's my point about about generated parsers. This pattern, everything before the comma here, was a specific rule that was reused in other places.
Okay.
It was reused in the place where we just allow the method call to the square equals method, to the square brackets method.
Yeah.
Right? Because if we have our own object, let's not call it that, and it has this internal hash. and you define
Oh
some
gosh. Yes. Okay, go for
you
it.
know,
I know
yeah,
what you're gonna do. Go. Yeah.
we
Yeah.
define a square brackets method that takes some keys, and it returns values of keys.
Okay.
And we define some square equals bracket method that has keys in the value. We're going to say, that's going to say values of keys equals value. Okay. My object.new. Now my object of foo returns nothing, but we can set the value here.
And now it'll return 1. Yep.
And now it'll return. But you can accept any number of values in here. Right?
Yeah.
And if we set that equal to 1 and we just look at it, you'll see that it's in there because we've defined that square brackets method.
Mm-hmm.
Now, the square brackets method can also accept a block. Like that.
Oh gosh.
Or like this. No problem. Now, they reused this rule in the grammar.
Okay.
Which means that if you do my object foo and you have some kind of block here, wrong object type. Oh, how recently did you build this?
This morning. Might be fixed.
I think they just removed it. Oh no, this might be the bug. They were trying to remove this because it had a bug in the implementation.
So you're doing 2 parameters here, a proc and a symbol and a block, or a proc, right?
A symbol and a block, yeah.
Okay.
Oh, that's funny. I think it worked in previous versions. Anyway, the point is, because this rule was reused, actually, let's see, equals, see if this works. No. Okay. Interesting. Okay, this worked the other day. But the point was, this
yes.
This rule explicitly allows doing this because it was reused in multiple places. As a handwritten parser, we can break those rules and only use them in certain places. No, you can do this with a generated parser, but it's like you have to be very vigilant.
Yeah.
And you have to be very careful about this. Whereas we know exactly what's happening here. You can also do like crazy stuff, like like this, and then my object of foo is going to be the error, and sometimes that works.
Gosh. Oh,
there you go. It's accepting a block still.
Wow. Oh gosh. You can also do, I think one that you and I were looking at the other day, which made me raise my eyebrows, is you can just do like a constant here too, like
oh yeah, totally,
foo, and now all of a sudden we've got foo as a constant.
Oh yeah, you can do that, but you can also do like dynamic constants.
Oh man.
Like if that object resolved to a class.
This is so I'm somewhat regretting doing this live stream because I don't want people to know that you can do you can do this.
Yeah. There's so much.
Oh,
target nodes are very, very powerful, but the overarching point of this whole thing was like, to answer your original question, why did I choose a handwritten parser?
Yes.
I wanted performance, I wanted error tolerance, and I wanted control. And that is why.
That is why. Okay. Let's see. Johnny Lee is asking, does every method in Ruby always have a block? Also, does amp is amp I can't read that in English. Amp curlies is fun for passing a block.
Oh, okay. So every method in Ruby always accepts a block. Yeah.
Yes.
You can put foo.
It always takes a block. Yeah.
No problem. The ampersand is an operator that calls to proc on an object if it's not already an object. So
I like that every method takes a block. You can use that. It's very nice for doing like code poetry.
Yeah.
Because you can just put anything. if the, for example, like puts isn't going to yield to the block, so you can just like throw stuff in there. Pointless one says, "Too late. Forbidden knowledge has escaped." Yes,
Yeah,
unfortunately, only on this live. Only the people who watch this. So there'll be like 5 people.
it's cool. It's cool.
Oh wow, nice.
Yeah. So the ampersand just calls 2proc. The more common way of doing this is calling it on a symbol. So if you does it not even parse it? Oh, I guess those are all method calls.
Yeah, it'll parse it. Those are all method calls. It's good.
Yeah. Yeah. The more common thing to see is like this.
Sure.
That is the ampersand that is calling 2proc. If you look at like symbol dot method 2proc, you'll see it like whoops.
Instance method.
Yeah, it exists.
Nice. I think that's one of the like. I think that came from Rails actually.
Oh really?
Yeah.
That was like a monkey patch.
Yeah, it was a monkey patch in Rails that made it upstream. Yeah.
Oh nice. That's awesome.
Okay, so
so that was off topic.
Yes, totally. So what, like, we talked about goals of the project. I'm gonna bring us back to intro screen here. We talked about goals of the project. How about where is Prism used today, or where is it used?
Yes, so Prism is a lot of things. So Prism is a gem that you can use on your own. You can install Prism, and you call prism.parse, and it gives you a tree, because I'm a tree data structure enthusiast. Big fan of tree data structures. Call prism.parse, gives you my favorite tree data structure. Yeah, so you can use it as a gem. It is also shipped as a C library within CRuby as of 3.3.
Okay.
So this is an important delineation where you can install Prism as like a default gem, and it is like a bundled gem, but then also Prism is just a standalone C library requiring no dependencies. So CRuby actually like basically vendors it, but also kind of not. Like it just like pulls it in and uses it. And if you do Ruby -- parser equals Prism, you can parse things with Prism.
So the idea with the standalone library is that you would be able to use this inside of, say, a Rust project or like anything, and it can be completely independent of Ruby.
Right. And in that vein, we have released two crates to Cargo, which are Ruby Prism and Ruby Prism Sys, that vendor the C library, and then allow you to call it using bindgen. So you can, and actually there are people that are using it for Rust tooling internal to like private to companies, but that's
awesome. That's really cool.
Yeah, and then it's actually been nice because those people in particular were really useful for performance because they were measuring a lot of performance stuff. So that was good. And then the guy behind Artichoke Ruby is looking at potentially using it at some point for Rust. It can also be used from JavaScript because we can cross-compile it to WASI, which is distinct from WASM, but only slightly.
Okay.
But anyway, it's basically the same thing, and it's a WASM module that is run by the WASI runtime. Anyway, so you can access it from @ruby/prism, the JavaScript package. So that's published on npm. And then Prism is also vendored into JRuby and TruffleRuby. They are using it we have the ability in Prism to serialize an AST to like a binary stream, and they are using it as their main parser. And in both of their next major releases, it's going to be the main parser,
right?
Which is exciting. And then the other one that is using it is Natalie, which is another Ruby runtime that he is using it by ahead of time compiling Ruby's the Prism's Ruby files to C++, and then calling the serialization library and that's how his parser works.
Interesting. Huh.
Yeah. And then the only other thing to mention is that there's another gem called Parser Prism, which allows you to compile Prism's AST into the Parser Gem's AST to make your Rubocop faster.
Wow.
And the people on the Rubocop team are actively trying to make that like
Right.
an option in Rubocop now.
So one of the big, like, huge advantages of Prism is that whenever we add new syntax, we can just we can drop, like, whenever CRuby adds new syntax, then JRuby and all the other Ruby implementations will get that for free. Well, they get it parsed for free. Their compiler may
Yeah.
not support it, but the parser supports it. So, like, I guess
Right.
the hard part is done for them, basically.
Yeah, and it's not even necessarily like the parsing itself that is the hard part. It's like parsing exactly in the same way
Mm-hmm.
that's the hard part, because like the people behind JRuby and TruffleRuby, they can like write parser generators all day or write parsers, but it's like the very specific, like, okay, if this particular byte is in this particular position, like getting it 100% compatible is very, very difficult, and they've never been 100% compatible. They've always had differences. So yeah.
Johnny Lee mentions that it sounds like something. So this serialization strategy sounds like something DRB could use to serialize across the network, which is kind of interesting to think about. I think you could.
Yeah.
So, like, for example, DRB, you can't, like, you can send objects across the network, some objects, but you can't send, like, say, a proc instance, for example.
Right.
Like, maybe you could parse the contents of a proc and send the AST across.
That would be wild.
Yes.
That would be wild. Yeah, we totally could.
Let's see. So you can use Prism today as a gem.
Yes.
Just install it if you want to. We should do that. Let's use it as a gem for a little bit. Just like parse some stuff, and then let's try fixing this bug.
Let's do it.
Sound good?
Yeah.
Okay. I'm gonna put us back over the desktop. All right. Let's see. So where the heck is my mouse? There we go. I guess we can get. Can we get Prism from this IRB?
Oh yeah, totally.
Oh, we should be able to, right? Because it's
require Prism. Yep.
I'm using Ruby. I'm using through the latest, like, I'm using Edge Ruby, so we have it. So we can do like Prism dot parse def foo. I don't know. Let's just do something easy, I guess. Oh, and look at that. It gives us a very nice abstract syntax tree printout.
It does.
That's great.
You'll notice it doesn't just return the node, it also returns a whole mess of other information as well. And that's kind of important.
Yeah. So we have, like, for example, we have, what is this? We got location information, so we know where the nodes were located. This is actually a span, right? Like this 1,0 and then 1,12. That's like the range of text that whole thing covers.
Yeah.
Interesting.
We also have, if you look up at the top of that, we have an array of comments. We also have data loc is the location of, if you use the __end __, it gives you that.
Oh, this is paging. I didn't realize that. Okay, yeah.
It gives you errors, warnings.
Interesting.
Magic comments.
So I could do like, let's do like prism.parse. Boy, I wish I could bring, let's see, prism.parse, and then put like a comment at the top of this. Oh, sure.
Just add a new line. You're all right. Yeah.
Yeah. Source statements. Where are the comments?
Up at the top.
There we go. Inline comment. Nice.
That's to delineate it from the equals begin and then equals end.
Yep. A blocky comment.
Blocky
awesome.
comment.
Blocky comment. That's awesome. Okay.
Yeah.
Neat. Also, you can use Prism from the command line.
It doesn't ship with the CLI. I mean, you can do it from Ruby if you want.
Yeah, you can do Ruby -- dump equals Prism parse tree, and it'll give you a parse tree, right? So I have like here. Let's look at this test code. So this test code actually, bat. There we go. Look at that. Nice.
Whoa.
Yeah, bat.
I don't think I've seen that before. Nice.
Yeah, print out some stuff and color, like make it colored. So we have this test code here, and we can like dump out the syntax tree for us. So I can say like mini ruby -- dump equals prism parse tree test code, and then it's very long and doesn't fit in my terminal, but there you go, you can do it. I'm
You
running it
can.
with mini Ruby here, but this is like you can just do this with Ruby, right? You can do
Yeah, you can do it with Ruby 3.3
3.3.
actually.
Yeah.
Yeah.
Okay, cool. So if you have Ruby 3.3, you can do this. Johnny Lee Rollins is asking, how does end work? Or
How does
in parsers, like how is that parsed out?
we just give you a location? So as soon as you have it in there, we're
Mhm.
just like, all right, we're done parsing the tree. Here it is, and then it just goes to the end of the file.
Oh, okay.
So we're just like, here it is. Do what you will.
So let's like we could do let's make a smaller file, small.rb. We'll just do like foo, just a method call, and
Yeah.
and then like that, something like that, and then
Yep.
we'll do.
That's not gonna give it to you. You got to parse it with So that's just displaying the actual AST, but the end is
Oh,
not part of the AST.
okay.
But if you go to the command, if you do like IRB and require Prism,
Okay.
then you do prism.parse file small.rb.
Parse file small.rb like that.
And you'll
There we
see
go.
data loc at the end. There's a span up at the top of right above, up. There it is.
Okay. Right.
Line 2, column 0 to line 4, column 0.
This thing right here. Yep.
That's the one.
Gotcha. Okay.
And then it's the consumer's responsibility to actually like put that into a.
Got it. Into a thing, right?
Into a thing. Yeah.
Okay.
Well, into the data constant if it's the main file.
Mm-hmm.
Otherwise, you can feel free to ignore it.
Cool. Let's I'm worried about time here. We only have 13 minutes left, so let's
do it.
Let's fix our thing. I wanted to show, so we're looking at this code here. This is our bug, and I wanted to show, like earlier in the stream I was talking about local variable storage, and like we were talking about IRB and local tables and stuff, and I want to show that. I actually want to show that here. Like you can take a look at it, because this is going to be key to fixing our bug here. I have an example here, test2.rb. So here we have a function that takes two parameters, a and b, and if we print out the instructions for this, I'm going to open a new terminal here. Test2.rb. If we print out the instruction sequences, we can see the local table. It prints out the local table for us right here. My little thing is getting in the way. Oops. Let's move this a little bit. All right, so right here is our local table. We know its size is 3 because we had three parameter. Wait, no, that's not true. We had 2 parameters, A and B, but there is a magic anonymous parameter here for keyword. This is to deal with keyword parameters. We can see A comes first in the local table, and then B comes second in the local table. Now, an interesting thing is, let's change A to have a default value. So let's say like A's default value is 1, and B is our acquired keyword parameter. So if we do that and reparse this file, actually I'm going to clear this so we can get it at the top of the screen here. If we reparse this file, we'll see that B has actually moved to the front of the local table. And the reason is, like, as we were talking about, locals come from the stack, so all the required ones have to come first in the stack. They all have to be pushed before we deal with any optional parameters. So we see that B comes first, even though we specified it second in the method signature. So can we compile this with Prism?
Should be able to.
We just do right. Yeah.
Dash parser.
Yeah, dash parser. Yep. Clear. Dash parser equals Prism. Let's look at that doesn't dump the iSeeks though.
No, just dash dump equals instructions.
Oh, okay.
There you go.
There we go. So we can
see that it's wrong.
Yeah, you can see. So we can see the bug here. Like if we look at this local table, we can see, hey, we got A at the beginning, so it's listed as A, B. When if we use the normal compiler, if we use Ruby's compiler, it should be BA. So this is our bug. In fact, like maybe I don't know, like our test code is I guess, more complicated than it needs to be. Let's make it, should we just make it simpler?
Yeah.
This, yeah.
Yeah.
Okay. And we call this like this. And if we run it, like, let's run it. If we run it, normally we get 1, 2. If we run it with Prism, we get an error. So let's go fix it. Let's see. All of the Prism compilation stuff is in prismcompile.c. One thing I like to do for fixing these issues is I'll print out the AST. How do we do that?
Dump equals parse tree.
Equals parse prism parse tree.
That one too. Yeah.
I like to look at the Prism parse tree, and then it tells you the node name, so you can see, like, for example, here we got a parameters node, like parameters node right there. So that's how we know, like, where in the compiler to look to fix stuff. So let's go do that. Actually, where is it going to be broken? It's going to be parameters node, isn't it?
I think it's going to be... Yeah, I think it's going to be in parameters node, but it might be actually in scope node.
Okay.
I think it's there. So we should explain what scope nodes are.
Yeah, so scope nodes are fake nodes that you'll never see in a parse tree, but we use them for making compilation easier. It's basically every time we enter a lexical scope, we'll create a new scope node and use that inside the compiler. So, like, for example, this method foo gets a scope node when we compile it. If we were to have like a block, we'll have a scope node in here. And this scope will point up at the top, like the foo's scope. And we use that for various stuff that I don't want to get into because we only got 8 minutes, dude.
We'll get it done.
Mark T is asking, Mark, hey, how's it going, Mark? What am I using for this pointer thing? I forgot the name of the app. Oh, it's called Screen Brush. Okay, let's find our parameters.
Keep going down.
Yes, happy New Year, Mark. Good to see you online. Let's see. We gotta find our keyword parameters, right? Here we go. Here they are. Keyword parameters.
Not yet.
Keywords list. Okay, we gotta keep going. Right here.
Yeah.
Here we go.
Yeah.
So we have to loop through all. Yeah, this is fun. We have to loop through all the keywords. All the keyword parameters, and then add them on. And if you read through Prism Compiler, you'll see we've commented this with like what stuff, like what it is that we're dealing with. Like it's got a little comment here, so you can go check that out. Let's see.
I would say as a dumb first pass.
Yes.
Let's copy paste this entire for loop twice.
Yes, I completely agree. Yep.
Okay.
Absolutely.
Great.
So the problem is that we're currently adding all parameters just in the order that we see them. What we need to do is we need to add all of the required parameters first, and then add all of the optional parameters last. So we're just going to copy paste this for loop and then do the required ones first and then do the optional ones second. I mean, make it work and then make it fast, right?
Yes.
So let's just not handle optionals.
Yeah, I mean, I think you can just make it an if statement at that point.
Yeah. So, wait, what the heck? This font is too big for me. Here we go.
Wait, I didn't even see. Did you copy paste it?
I did copy paste
okay, great.
it. I'm going to delete this. So we can just be like...
There's a macro you can use called PM node type P.
Oh yeah, let's do it. If PM node type P, P keyword parameter node, and then it's PM required. That's pretty wordy. Okay, and then we'll get rid of this switch statement.
Keep the comment. The comment's nice.
Yes. We like the comment.
I like the comment.
Okay. And then
Done with
that.
That all goes away.
Yeah, done with that one. Wait, what's this? We need this.
We need that.
Yep.
We need that. That actually puts it into the local table.
Yeah, this code right here puts the value into the local table. Let's see. Mitchell is saying he's writing a Pratt parser for Elixir and discovered Prism after that and felt confident after seeing it was also a Pratt parser.
There you go.
Yeah.
We will talk about that next time. Okay, wait, go back. You're going to need to put all that inside the if statement because we don't want to insert if it's not.
What stuff? This stuff.
Those three
Yeah,
lines.
totally. Yep. Thank you.
Yeah.
And actually, okay, so then we're going to do the same thing here, but we just want to do optionals. So, you know what I'm going to do? We can probably... Oh, no. Optionals seem a little bit more complicated, huh?
They have a type that goes into either a hash or the... Yeah.
Okay. I'm just going to grab this if statement.
Yeah.
Put it here. What is our, like...
PM optional keyword parameter node.
Optional keyword parameter node. Great. Keep our comment.
Love the comment.
Love the comment. I like these comments. These are great comments. And then we need this whole case statement, right?
Yeah, basically everything in there.
Okay. Boop. Put it in here. And then...
Get rid of the break.
Yes. Hold on. I'm going to delete the switch statement. Switch goes away. Break goes away. These go up here.
Mm-hmm.
Oops. No, I don't want an arrow tool. Stop. I want to do equal to... There we go. Okay.
Run
Did we do it? Did we do it?
I think we did it.
Okay, let's give it a whirl. Just gonna make mini Ruby, and then we'll just check this test code, right?
Not the parse tree. You're dumping
right.
the parse
Oops. Thank you.
dump the instructions.
Yeah. Mini Ruby.
Yeah.
Like this. That's not right.
We were close. We got B first. B first is good.
Okay, what did we do wrong?
What did we do wrong?
What did we do wrong? Let's see. I'm gonna get rid of that. And actually, I'm gonna... This font is killing me. Make this smaller. Okay. Let's see.
Go back up to the if keyword list and keyword size. Yeah. Okay.
Okay.
We allocate this array of IDs, which works.
That's fine. Yep.
For I is wrong. I is wrong. Because if we have optionals and keywords, we can't reuse the same I. We need a different counter that we increment.
Yeah. We got to keep incrementing them. Yep. Oh well.
This can just be used to get the nodes out. That's fine. Oh, also local index plus plus. That's not right.
No, that is right. That's right for sure.
No, because we're gonna go through.
Oh yeah. You're absolutely right. We can't. Yep.
Yeah.
That's too bad.
Fancy for loops.
Yeah, and we're gonna have to do this down here as well.
Yep. Right. Get it out of the for loop. Yeah.
Yeah. And then what? I is
just for the nodes. So we want
just for the nodes. Yeah.
We want a different. We want make a keywords index like size T or something above.
Okay.
And we'll just increment it. Unless you want to be really fancy, what you could do is just keep an offset from local index. You know what I mean? Because local index is always going to be incremented every one time. But you could do like whatever minus local index, but that feels a little fancy. It's probably fine just to have our own counter.
I'm not following you, so.
Oh, sorry. So you know how we're only incrementing local index every time we get a new keyword?
Yeah.
So instead of, right, this can be keyword index plus plus, but this could also be like.
I see what you're saying. Yep.
Yeah.
Yep.
But this is also clear.
Yeah, let's do this. I like that. Ah! Yep.
Okay.
Yeah, I like that. KW index plus.
Cool.
Make mini Ruby. Let's try this again. Oh boy, we're over time.
We did it. We did it.
We did it.
Yay.
Yay. We did it.
Just in the nick of late.
Yes.
Yeah.
Awesome. Let's see. I'm gonna bring you back on for a second. Kevin, thank you so much for coming on. I really appreciate it.
Yeah.
I think now that, like, I know you're a tree data structure enthusiast, but I feel like maybe you ought to branch out. Sorry.
Excellent.
I had to.
Good.
Thanks for coming on. I am going to go back to slides now and then say some stuff. So thank you so much for being here.
Thanks for having me.
Bye. Let's see. Keynote. We did Kevin came on. We did that. Let me get back to Keynote. We hacked. We already did that. This was our bug. We fixed it. Though we did golf down the problem. And I just want to say, like, thanks everyone for coming. Really appreciate it. I had a fun time. It was good. I really enjoy streaming, so thank you all for coming here. I really appreciate it. I'm off next month. I'm not going to stream in February, so I will see you all in March. Thank you all so much for coming, and I am going to sign off. Happy Friday, everybody. Bye.